9.2. SDLC development. So the last lecture was all about design. It was about making you want to think about how your code is structured better. More so than how it's written, right? Like the actual development part. So safety and type checking. What's one of the first things you noticed when you programmed in C and then Python, right? Probably one of the first things you noticed, besides the indentation, which I'm sure many of you were like, it's the typing. It's the fact that in C you've got, ints, chars, doubles, char stars, all of these different types that are very rigid. They have specific amounts of memory that are used for them. And then when it comes to Python, it's all like, whatever, man, just give me some stuff and I'll just, deal with it for you. So we're going to talk about type checking. Now, when we say safety is such a funny word to use with software, isn't it? Like software safety, like what does that even mean? Do you put a padlock on your computer which has your code on it? It's like, no, like software safety is about making sure that your software, think of it a little bit like testing. It's about making sure that it works. It's not broken. So type checking and all this is around that topic. So software safety is formally defined as a protection from accidental misuse. So why do we, what does that actually mean, accidental misuse? Well, an example is in Python, you can multiply a string by a number, right? That's not good. That could be accidental misuse of a string or a number. If you try to do that in C, you would be told to convert them first. They're not the same type. You can't do anything with that. So safety is about protection from accidental misuse, from programmers writing bad code accidentally because there aren't as many safety checks in them, right? Like what is safety? You think about like safety in a workplace. You think about like a hard hat and you think about a uniform and protective gear or something. The same kind of principles can be applied to code. Whereas software security on the other side, which is maybe what you thought about when I said safety, is a protection from deliberate misuse, right? So that's cybersecurity, making sure that people don't do anything malicious with your code. So, safety is about preventing errors. It's about preventing accidental errors. This is a case study that another old tutor, Rob, found, which is that around 94% of spreadsheets, Google Docs, like Google Sheets or Microsoft Excel, contain errors in them somewhere. And that for any given spreadsheet formula, right, every time you go and type in a formula into the top of, Excel, the thing up here where you're like equals sum of whatever, there's a 1% chance that every formula contains an error, right? And it's like, why does it contain that error? Well, it's because if you think about Excel, there's a lot that you can type in that's not valid. You can reference cells that don't exist, right? You can write formulas that aren't valid and it just comes up with error or something. And this kind of comes back to this idea about compile time and runtime, which is a really important concept to understand as a software developer, which is like there are compile time checks and then there are runtime checks, right? And a runtime check is an exception. It's something that is checked. It is some things you're trying to make sure the software is safe while it's running, as opposed to compile time checks, which is before it's running, right? So in C, you can't do a lot of things. GCC, DCC goes like angry, and that's because it's trying to prevent things going wrong. So there are things that can go wrong in languages like C, and there are things that can go wrong in languages like Python. For instance, in C, you're able to read from memory that hasn't been initialized yet. You can do that, right? That is a, what do we call it? Accidental use of the language. You can dereference a null pointer. You can put an asterisk out front of a null pointer and you'll get a seg fault or something like that. You can use memory after it's been freed. You can write outside the bounds of an array. If you have an array of 10 ints, you can write into the 11th int. Something crazy might happen. And you can forget to free allocated memory. These are all sources of accidental misuse of the language that don't have great safety measures put in place, right? As in, there's not things to stop you. There are things to, like, but there are plenty of things that C stops you doing, right? Like, you can't assign a string to an int. You can't plus a string value. You can't yeah, there's random stuff, right? Like, every compile error you've gotten is the language stopping you. Whereas and then Python has different things, right? So in Python you can access a variable that hasn't been initialized yet. Sometimes, depends on the interpreter and stuff, but it's like in C you literally can't use a variable at all under any circumstances. You can't say cat equals Sally without, like, you can do that in Python without having to declare it as a string, right? And this can lead to some strange behavior in Python, right? Because someone comes along and changes cat from Sally to cat 52, and suddenly all of the assumptions the rest of the program have been operating on don't work anymore. And you also probably know this from your own experience. It's like, because Python doesn't have any type checking, you can literally just pass a function something it doesn't expect. So if your function expects a string, you can just give that function a tuple or something, right? It might fail, but it will still run first, right? Like, it doesn't compile fail like in C. Like in C, if you try and pass a string into a function that expects an int, it won't compile, right? There are safety measures in place to prevent compilation. Compile time, again, I'll just stress this 1,000 times to you. You want, in a perfect world, right, which we might get to in the future, everything that goes wrong in a programming language, everything you do that's bad, all of these safety checks that exist should happen at compile time in a perfect world. Before any codes run, before anything bad can happen. We don't like it happening at runtime, but it is inevitable. This is what I've just been talking about, sorry. It's like, so when we talk about compile time, we talk about things that can be inferred without the executing of the code, e.g. Pylint, right? Like, Pylint, again, doesn't run your code, it just looks at your code. Dynamic stuff, though, are things that are checked during execution. The most simple example is in Python, you have exceptions, right? Try and except. These things aren't done at compile time, right? It's not a check at compile time to check that this thing went wrong. It's you putting code together in the runnable that just runs and is watching it while it runs, right? It's keeping an eye on it. So we want to always move things from dynamic to static wherever possible. Static safe, static easy, static clear, static wonderful. We love static. Catherine asks, are we going to be marked on complexity in iteration 3? No. Like, if your code's a mess, yes, but like not in relation to things that have been in the lecture. No. Which I assume is what you're asking, essentially. Okay. So memory safety is a topic that you're probably familiar with. And I want to just, like, it's really interesting to compare Python and C, because you know that C is not a very memory safe program. You can do some crazy things with C, right? You can write into arrays that you didn't allocate, and there's a lot of strange bugs and security flaws that come from that. Whereas Python is memory safe because it prevents you accessing memory directly, right? You think, like, Python uses pointers, it just doesn't let you touch them because it doesn't trust you, right? It thinks like, it's like, hey, you just go over there and tell me the logic. I'll go write the damn pointers, because if I look after it, I can make sure that it's all freed. I can do all of that. Now, if you've done other courses like 2511 with Java, they might have talked about this. But essentially in Python, what happens is things are malloc, things are freed all the time. You just don't see it because there's an abstraction of this, of Python managing it. Now, because Python is managing these things, any type of abstraction, nearly every type of abstraction, adds overhead. It adds a performance cost. Because every time in Python, right, like, think about this, in C, when you write code, when you say like, haven't written C in like forever. When you say like int A4 and you declare like 4 integers like that, and then you say, printf A1 or like A5, there are no safety checks in C at all. Nothing. C will take you literally. It will literally go and get the address that A points to, and it will move 5 integers worth of memory ahead, and it will try and print whatever the hell that is. And it might print random stuff, it might segfault, like lots of things could happen. But in Python, what happens is if in Python you say like, A equals some list of 4 elements, and you say print A5, Python under the hood actually does some things. It actually goes and looks at the length of the A list, and it checks what index you gave it. And if you gave it a bad index, it'll raise an exception. It goes up, index out of bounds error. And that's great because that makes Python memory safe. But the downside, though, of course, is that it's slower. There's more that happens. Every single time you access an array element or a list element, Python does that check at runtime, right? Some things you can't move to compile time. For example, if you're reading from a file or you're getting data from a front end, like a message, you don't know how big that character array is at compile time. Like you don't, because it depends on the person actually sending it, which can vary. You can't predict the future, right? So moving everything to compile time isn't always possible. And an example is memory safety is really hard to move to compile time. So in this case, Python has said, we're going to prioritize memory safety over the negligible performance cost of bounds checking. Because bounds checking, takes some takes some effort. We've just talked about this. I've just gone through that. Great. So that's memory safety. Then we have runtime errors, right? How are these dealt with differently between different languages? Okay, so, and this is kind of an important conceptual point. So Python uses exceptions. For instance, if you try and access the fish key of the animals dictionary, what happens is that Python throws an error. It throws a key error. It raises key error, right? Again, we've talked about exceptions weeks ago. It screams and it waits for someone to catch key errors. So that happens in Python. C does not support exceptions. I don't know why. My guess is that the problem with exceptions is that they disrupt the normal flow of the program. Because normally programs can follow, like normally with a program you could draw a pen on the page and follow it. You know what I mean? Like you go through this function and then like through that function and through that loop. Exceptions kind of change the behavior of how code flows. And I think C tries to be very simple in that sense. So the way you deal with errors in C is very different. How you deal with them in Python is this fairly standard principle of like seek forgiveness, not permission. And the idea is that in Python, you don't always check if you can do something. Sometimes you just leap and say, I'm going to go do this. And then someone who's you're asking to do that will start screaming and say, you can't do that. And then you catch an exception, right? So you aren't saying, can I do this? You're saying, I'm going to go do that. Tell me if there's an issue with that. And then it's like, there is an issue with that. And then you catch an exception. And that's what this example is up here. Animals, fish. You say, hey, I'm going to go and get that key, right? Thanks. Okay, I got that. And then the interpreter's like, whatever the hell people say. So that's what Python does. It encourages you to assume that something will work and deal with the case that doesn't work, right? Try, accept. The benefit of this is that it can simplify the logic of your code substantially, right? C code can be really complex doing all these checks everywhere, whereas sometimes it's easier just to say, I'm going to take your input, I'm going to cast it to an integer, and if it doesn't work, I'll do this, rather than like, if that, do this, like whatever. So it can definitely simplify the logic in terms of readability and understanding. And And you can also handle multiple types of errors really easily, right? Like exceptions are very powerful. The downside of this approach with exceptions is that it makes the code non-structured. We talked about that. That's because the code doesn't always follow the linear flow, and that also leads it to be harder to reason what code will be executed. Again, you can't just follow code and be like, this is the exact flow because it starts at the top and it finishes at the bottom. That's why when you first learn C, they teach you things like only have one return statement, because early return statements also make it harder to reason what code will be executed. Because maybe you'll quit here, maybe you'll quit there, like I don't know. Whereas if you just have code with no exceptions and no early returns, and your code is made up of functions, your code always starts here and finishes there, and you just have to figure out what loopity-doopity it does along the way. So we like code being easy to reason with and being structured. So there's the con of this approach with Python. The other approach, which is the C style approach, is look before you leap, right? As in, like, you don't want to do anything until you're sure you can do it. You don't index an array until you've looked up how big that array is. That's your job, not Python's job. You don't do that and wait for it to scream at you. You do that. So this approach encourages you to check something before you can do it. The benefit, it doesn't require exceptions, which can make the language simpler. And the code is structured, so you can reason about it. And what's the downside? The core logic has been obscured by error checks, right? It's harder to figure out what's happening. So the complete opposite, right? There's pros and cons of the opposite here. Really interesting stuff. Okay, so this lecture is predominantly about safety, like how do we ensure safety, and about how like exceptions and asserts and all these other things differ. And then we're going to talk about static type checking. Before we do talk about static type checking, which is only going to be like 5 or 10 minutes, I will give you all a quick 5-minute break now, because I know some people have been here since 11 as well, watching the bonus lecture. Unless people just want to power through, would people like a break? Just waiting for the lag to catch up. Okay, let's take a 5-minute break, and then we will keep going with the rest of safety. Cool. Okay, thanks everyone. Damn it. Hi. I'm sorry. I'll have to trim that out in the recording. Yes, you are deaf. You are deaf. Okay, so last thing we're talking about is removing errors statically. So I've said to you at the start, we want to move errors from runtime to compile time, because the more errors are in compile time, generally the better things go. We are able to prevent more bugs. And when things fail in runtime, there's always the chance they go wrong. But like, you can't really get hacked at you can't really get hacked at compile time anywhere near as easily. So we've talked about this, right? We don't like runtime. There's a lot of aspects of Python. The most common thing to check at runtime, which is the remover of bugs, is type checking or type safety, right? Type safety refers to making sure that people don't unintentionally use types incorrectly. So type safety in languages like Python, right? You're preventing mismatches between the actual and expected types of variables. So C is type safe, as you have to declare all your types to the compiler. So at compile time, the compiler always knows all of your types that you're going to use. Whereas languages like Python, other scripting languages, they don't have this. The type is not known until the program is executed. So you have your kind of more strict languages like C, Java, Haskell, which have built-in static type checking, and that's just how the language is designed. You have other languages like Objective-C and TypeScript, which is a superset of JavaScript, where the type checking doesn't exist in the main language, but it's kind of like a feature easily built on top of it, right? So it's built into the language. You don't have to pip3 install something. It's just part of the language. It's just you can turn it off. And then you have languages that have external type checkers that you can work with but aren't part of the language. And Python is an example of that latter one, which is what we're going to talk about, which is MyPy. So MyPy is a optional static type checker for Python, where essentially, rather than writing a Fibonacci generator here, we're going to talk about generators next week, you can statically type this and say, you know what, my Fibonacci function takes in an n, which is an int, and I expect it to return an iterator type of an int. Now, we're not familiar with what these types are, but there might be some other examples we can look at in our lectures, for instance. So MyPy is a type checker for Python. It's a little bit weird, I think, because I think in Python, right, if we take this code here, let's maybe try and open up week 9, see if it's floating there. Yep, so I've got the finished code here. Oops. Okay, so this is what the code looks like without type checking. I'm pretty sure that the way Python works is that it's actually like if I run this in a terminal, I go Python 3 safety, it works, and I'm pretty sure if I add int like this, it still works. Oh, the file's frozen saving. Oh no, this isn't good. Yeah, Python interprets on the fly. There is no static. I mean, there's some basic static checks in Python, right? Like indentation errors. That's kind of a compile error. It won't run your code if it detects. So Python will, like, when you run a Python file, it'll import everything and like do a sweep to check some basics. Then it'll run it. So there are some compile time checks. There are some static checks. But PyLint is run before any of that anyway. Like PyLint's like an external runner. Most linters are run external to compilation and running. With Python, you can add types to, say, function parameters and to function return values without MyPy, right? You can just do that. It's a form of annotation. It helps people understand what you're doing. So for instance, we have this function called count, which takes a haystack, a big string, takes a needle, a small string, and it goes through, which is like a single character in this case, and it goes through that haystack and it counts how many times it exists. So a function like this is probably going to return an int, right? I have a big string, I see count how many times the little string appears in it, and then I return a number. I can do this in Python, and this is fine. This is like part of the Python syntax, but I'm not doing any checking with this. So if I want to do that, that's where I actually have to use MyPy. So what MyPy enables me to do is, if I install it and run it, which I can't remember off the top of my head. Ooh. So it'd be like run MyPy. I don't think I wrote it in the slides, did I? No, I didn't. So running MyPy and managing exports. Yeah, so MyPy is a module that it's a little bit like PyLint, right? So PyLint you can actually install with pip3. It just happens that we run it on the terminal. So like MyPy, I'm pretty sure is installed already because it's part of that list of things we got you to install, but normally you can just install it like this. and it will install. But again, if you've done that, I'm pretty sure we included in the main requirements file. So Josh says, are type hints just for readability? Yeah, they are just for readability. So you can include these anyway in your code, for sure. But, you know, if you actually want to use it to then check your code, then that's when you can use MyPy. So what I do with MyPy here is I can run MyPy on safety.py, and it will look at the type annotations and look at how it's used, and it will make sure it works fine. So for instance, like I'll give you an example. If I just pass in a 5 here, this should validly compile. It's just it'll fail when it runs. Oh, if I even freaking worse. This is horrible. This is even worse, right? Like there's a hierarchy of errors that you encounter in your life, and it's like the best kind of error is a static compile error, because they're clear, they're easy, there's very little risk. Then there's runtime errors where your program fails, division by 0, tan of 90 degrees, exceptions, right? Square root of a negative number. All of these things, they crash your program at runtime, seg faults. Then the worst type of error that exists are logic errors, or errors defined by undefined errors described as undefined behavior, which are when things seem like they work. So in this case here, we have passed a number into this function, which will never return anything other than 0, because there is no character in a string. Hate hen. I don't think I wrote this example. Whoever that person is, I'll find them. You know, it's like, this will always be 0. So while the Python thing runs fine, when we run MyPy will detect, hey, argument 1 to count here is has incompatible type int. It expected a string. So MyPy can be very powerful preventing types of errors like this. Then when we run it, we get 2. Perfect. And then same thing here. So what does search do? Search takes in a haystack, which is a string, takes in a needle, which is a character. In Python, I don't know how easily you can distinguish between characters and strings, but and then we loop through it, and if we find the needle, it returns the needle itself. So for instance here, if I search for H in Hade hen, it gives me an H, right? It found the H. Basically, it returns the needle if it finds the needle, but if it can't find the needle, it returns none. So how do we describe this return type? Well, in Python typing, there is a type called optional, and what optional is it's a type whereby you give it the type in the brackets, like this, and basically, this is saying now that the type returned is either a string or it's none. So optional is in like, it's optionally a string. It might be the type you give me, or it might be none. So optional does that for us. So now when I MyPy this, we should have no errors. Someone, Yuval asked before, will this count as extra feature if we statically type check our function parameters and return types? Yeah, for sure. Yeah. It's probably a cool idea. Probably helps your code. I mean, yes. Short answer, yes. I know we say extra features. We should really call it bonus work or something, but how many marks? I don't know. It's again that thing, like it's going to be based on how much time it took. The more complex it is, the more marks you get, because your tutor will look at it again. They'll look at what you've done. They'll think about themselves doing that, and they'll think, would that have taken me a long time, or would that have been pretty quick? So, you know, if it's something that you could do for your whole code base in an hour, I wouldn't expect that you'd get a ton of marks for it. Whereas if it's a lot more, you maybe, you know, so just keep that into account. Great. That's it. That's the whole topic. So we like type safety. It's generally always good to program with type safe code, whether it's Python or something else. Yeah. Any questions about this? I mean, that's actually all we have for today, so I'll send out the poll too. Okay, poll for this lecture. Great. Anything else? Does anything else? Anyone has any questions about this? Otherwise, we can give you some early freedom today. Um, Reese says, how would you use typing to declare something as an iterable? Well, I mean, I think the example on the MyPy website had that. I think this function returns a Python iterator. The yield, we're going to talk about generators next week. But yeah, so you would just, it would be an iterator type. Iterators are a bit strange in Python, I think. Oh, Lab 9. Which one? Which exercise in Lab 9? Deploy requires iterator types? Oh. Oh, sure. I think that in this case, the actual type of the parameter would be an iterator or something else. Like, I mean, Griffin's got a comment there. Oh yeah, typing library. Yeah, I mean, it's stuff like this. Honestly, like, and anyone else would be googling it too, right? So, I think in terms of the question, when they say here, you can use the typing module. I'm pretty sure that there'd be a module that basically has some extra types in it that aren't part of like Python core potentially, might be my guess. Yeah, so like I think if you tried to do some of these things without the typing library, Python just would be like, oh, what are you talking about? I don't know what the hell you're talking about. So yeah, fun little thing. Maybe just on deployment, maybe I'll separate this out.